This is lecture 4. We will be discussing about ray diagrams for spherical mirrors for image formation, looking at refraction through plane boundaries as well as spherical boundaries. And thereon, we will discuss about lenses, the Lensmaker equation, as well as the thin lens equation, and we will derive those equations. Let's start with ray diagrams for spherical mirrors. In this case, this is a concave mirror. Basically, to locate where's the image, we need two rays, and if we can find the intersection of those two rays, then we would be able to locate the image. For example, for this concave mirror, so this is the curvature of the mirror. Let's say, and it has a focal point, and 2 times the focal length, you have the center of curvature. So let's say we have an object over here, and all you need is 2 rays. So we have a ray that comes from infinity parallel to the optical axis. This is the optical axis. So here it comes, and then after reflection, it will go through the focus point. And then another ray would be a ray that you can draw from the tip of the object, passes through the focal point, hits the mirror, and gets reflected. And it will be reflected in a direction which is parallel to the optical axis. So at this point of intersection, that's where you locate the image. There's another ray which I think is easy to draw as well. That's the ray that you will align from the top of the object to the center of curvature. And this line being passing through the center of curvature is basically the radial line. So it will then arrive at the mirror, gets reflected on itself, because here it will be a normal incidence, and it will meet at this intersection point. Here, in this case, the image form is real. For a virtual image formation, that's the condition where the object is placed in front of the mirror, but the distance from the mirror will be less than the focal length. So for this one, again, we have the ray 1, which is parallel to the optic axis and gets reflected through the focal point. And then another ray, let's now take the one that goes through the center of curvature. So from the tip here, you align it to the center of curvature, you draw this line and gets reflected back. But there is no, they don't meet over here. So what we have to do is to extend backward, and that's where they meet, and then we locate the image. Of course, we still have the third ray, or rather in this case, I'm calling it second ray. So this is the ray that you align it to the focal point, but it's leaving the object to the mirror. So whatever is behind, we make dashed line, because this ray is traveling from the tip of the object and gets reflected, and then it will travel parallel to the optic axis. Projected backwards, it also meets at the same intersection point. In this case, the image is formed behind the mirror, so it's a virtual image. Now, in the case of a convex mirror, the image form is always virtual. So no matter where you put the object, so it does not matter, but what we need to define is still the focal point and the center of curvature. So curvature is this direction, so we have, is curved this way, so we have the center of curvature over here. So the first ray is this one that comes parallel to the optic axis, and it will then arrive at the mirror and gets reflected. When it gets reflected, it is in a direction that's aligned to the focal point. And then the second ray will be the one that you can align it to the focal point, and then gets reflected at the mirror, and then it gets, the reflected ray will be parallel to the optic axis. The third one would be the one that is aligned to the center of curvature, and it reflects on itself. Now all these rays on this side, they don't meet. And so what we have to do is we have to project it behind the mirror. So when you project behind the mirror, it will be dashed lines. So at a point of intersection, that's where you locate the image. Now, if you are drawing the ray diagram and we are assuming para-axial rays, and let's say you do not have a compass, so we don't need to draw this curvature. What we do is we can represent this mirror by a straight line. So you just use a ruler, you draw the straight line. I'll show you in the next slide. See? Same, these are the same arrangement as in the slide before, but instead of the line that represents the mirror, we're going to draw a straight line. Now, this is valid if we are talking about para-axial rays, because near the axis is quite close to being a straight line here. So what we do the same thing. Now, you're given an object over here. You draw the first ray, parallel, reflected, pass through the focus point. You draw the second ray, pass through the focus point, get reflected parallel to the optical axis. We only need two rays to locate the image. So the intersection point here will help you to locate the image. And then the third ray that you can use is the one that is aligned to the center of curvature and then reflects on itself. Again, it passes through the same intersection point. Actually, just two rays is enough. Whichever you are familiar with, whichever you're comfortable with, you can choose either of this pair. For the other example that forms a virtual image, so we have the object, that's the first ray, and now I'm going to do the second ray that represents the one that passes through the center of curvature. And it doesn't meet over here, so we have to project backwards. We project the reflected ray backwards, and that's where we locate the image. Or you can also use the third ray. Again, you have to project backwards. The reflected ray project backwards, it also meet at the same point. Now for the convex mirror, same thing we do. But of course, initially you've got to mark the focal point and the center of curvature. So object, the first ray, okay, we need to project because we are aligning towards the focal point here to draw this ray. And then I'm putting the third ray first, which is the one that is aligned to the center of curvature. So this is where they meet. This is where I locate the image. Or you can use the other ray. Again, the ray that is coming over here, we align to the focal point and gets reflected parallel to the optical axis. But in this case, we have to project the reflected ray backwards to locate the image. Okay, this is what we have done actually in lecture 2. So I just go through very fast and briefly. Now, when we talk about external refraction, that is when the ray is coming from N1 going to N2 and N1 is smaller than N2. Now, the refracted ray will bend away from the boundary, or other words, towards the normal. They bend closer to the normal. Now, for the internal refraction transmission, in that sense, then we have N1 larger than N2. So the ray will bend further away from the normal or towards the boundary. And at a certain point, then the refracted ray will be traveling along the boundary. And that's where we locate the critical angle, which you already know. Now, any ray that enters at normal will not bend. It just go pass straight through. So this is critical angle. Now, it is defined by arc sine of the ratio of N2 over N1. And this is a diagram that will show you that this is θ1, that's incidence angle. This is refracted angle. And you'll find that for external refraction, the relationship will follow this curve. Internal refraction, it will follow this curve. And you'll find that basically this and this are mirror image of each other, whereby the mirror is placed along this diagonal line. And this is also a recap of what we did in lecture 2 quickly. So total internal refraction will occur when the incident angle is larger than the critical angle. So the ray will not be able to escape at all. You have total internal reflection. And in this case, we also learned that before, the internal reflection, not refract, reflection, the reflected ray will not undergo a phase shift. But if it is external reflection, there's a phase shift of pi over 2, okay? The examples of this, of in total internal reflection is, in this case here, is one example where that occurs. That's where we have a prism and this ray comes in. This prism has an inclined angle of 45. It comes in parallel to the base, gets reflected and internally, and then goes out. Now, diamond has this very beautiful colored luster. So basically, why does it catch your eye is because of total internal reflected ray. Now here, just an example. Now the diamond has to be properly cut actually. If it's a raw diamond, you probably won't see it so well. But because the craftsman that polishes and cut the diamond, if he's very, very skillful, he'll make a beautiful diamond that really catches and sparkles. So here we have white light coming in, and then you have total internal reflection, another one, and then it goes out. But because it's passing through a medium, so there's dispersion. So the colors, the component colors of white light will get separated. That's why you see colored faces depending on the cut. So you'll see colors, which are the component colors of dispersed colors here of white light. Another useful application for total internal reflection would be bringing the light through an optical fiber. Okay, so that's how you can get light propagating through the optical fiber. Now next, we talk about beam splitter. Basically, from the name, you know that it is splitting the beam. But it can also be used to combine two beams into one. As you can see over here, you have a beam coming from here, a beam coming from here. This one gets transmitted because it's partially transmitting and reflecting. And this beam that comes here gets reflected, so they are combined. But in this case, the beam comes from here, from the left, and then it goes, part of it is reflected and part of it is transmitted. So this one gets divided. It's usually constructed by depositing a very thin layer, which is semi-transparent. It can be a metallic or a dielectric film, and that will give you a partially reflective mirror. In fact, a very thin glass plate like the cover slip of the microscopic slide, you also can see this. You get partly reflected, partly transmitted. And prism also can be used as a beam splitter. For example, if you look at this arrangement here, like incident light coming in. So at this, there's two prisms here, combined as one. So at this interface here, part of it is reflected and part of it is transmitted. Let's derive the refracting equation for a spherical boundary. So let's consider here optical axis here, and this is our refracting surface or interface, and it is a circle. A part of a circle is an arc that we draw, whereby this will be the center of curvature. And let's say we have an object on the optical axis at O here, and this ray from the object goes along the optical axis and gets transmitted through the thin lens along the optical axis. So that's one ray. Okay, so this point where the optical axis meets the refracting surface, that's where we call the vertex. And this ray will arrive at the refracting surface at point P. Now at point P, we have Snell's law that's applicable. So we will have, now on this side, the medium refractive index is N1. And on the other side of the refracting surface, we have N2. So we're going to define θ1 incident angle now. Incident angle is relative to the normal. So we need to draw a line, a normal line to this surface at point P. So this line will be from P to the center of curvature. It is the radial line. So therefore, this will be θ1. And we are assuming that N2 is larger than N1. So this ray will bend closer to the normal. So we have theta 2 over here. And we will assume para-axial rays. So in other words, we are going to talk about small angle approximation. And we can then write it as n1 theta 1 equals n2 theta 2. And theta 1 and theta 2 also can be approximated to its tangent value as well. So we substitute for the theta 1 and theta 2 with angles that are given in this diagram here. So I'm going to show you what are those angles. So this ray that left, that started from the object point towards point P, is inclined at an angle alpha with the optical axis. This transmitted ray projected backwards, it makes an angle alpha prime with the optical axis. And the normal, which is from the center of curvature, makes an angle phi with the optical axis. So with these angles defined, then you'll find that theta 1 is actually equals to, well, we have over here alpha minus phi, because the external angle is equals to the sum of the two opposite internal angles. And theta 2, then we will look at this triangle. So theta 2 will be alpha prime minus phi. And over here, we're talking about para-axial rays, small angle approximation. So basically, this is an exaggerated drawing so that we can see all this angle and distance clearly. So if this point is very, very close to the optical axis, whereby these angles are really small, then you'll find that when you drop a line from P to the perpendicular to the optical axis, then point Q will be almost overlapping, will be on top of V. So we can then neglect this distance. So having said that, then in this case, O to V would be the object distance. Over here, when we project backwards the refracted ray, and when it cuts the optical axis, and that's also where the refracted ray here, if you project backwards the other ray, so they meet at this point here, so that's where we locate the image. So this will be the image distance S prime, and from here to here would be the radius of curvature. Now, so we, instead of alpha here, then we write small angle approximation is approximated to tangent alpha, and that will be equals to H over S. And for phi here, it will be H over R. Now we're going to take the absolute value first because we'll have to consider the sign convention later. And for the other one, that is the image distance, which is alpha prime, it will be H over S prime. Next, H was a common factor here. We can then remove it, and we are left with N1 over S and N2 minus N2 over S prime will be equal to N1. Now this term 1 over R here is common. Then you have N1 minus N2 over R. And using the sign convention that we adopt for mirrors, then we can rewrite this equation in this form, whereby it becomes N1 over S plus N2 over S prime equals to here N2 minus N1 over R. Basically, if you think about sign convention, let's look at this way. This is a refracting surface. If my image is formed on the same side of the object, it will be virtual. So S prime is actually a negative value. So that's why here it becomes positive. And then on the radius of curvature, which is center of curvature is on the left side. So that will be taking a negative value. So this will be negative. Then if we rewrite this as N2 minus N1, then it can remain as positive over here. Now, this expression here is actually equals to the power of the refracting surface. Then what about the lateral magnification of this surface? Then in that case, we have to draw an object with a certain height, and then we consider the ray from the object that passes through the vertex, arrives at the vertex at incident angle θ1, and it will bend. This was governed by Snell's law with θ2 here. And the other ray will be the ray that passes through the refracting surface and pass through the center of curvature. Now, this ray will not be deviated, will not bend, because it is at normal incidence. So when these two rays meet, that's where we locate the image, and we give it hi as the height. Okay, so from Snell's law, we will have n1 sine theta equals to n2 sine θ2. So small angle approximation will give us n1 θ1 equals to n2 θ2. And from here, θ1, since it's small angle, it can be approximated to its tangent, that is h0 over s. Over here, θ2 can be approximated to hi over s prime. And for lateral magnification, it is given by the ratio of the image height to the object height. And that will be equal to, now, hi over h0 will be n1 s prime divided by n2 s. And we inserted a negative sign here because of the sign convention that we have adopted. These are the sign convention for the spherical refracting surface. If the object is real, the distance will be s and the object is on the left of the vertex. If it's virtual, the value will be negative. Object is on the right of the vertex. For the image, it will be real if it's formed on the right side of the vertex and you have a positive distance. It will be virtual if it's formed on the same side of the object, which is on the left of vertex, then the value will be negative. For the radius of curvature, it is similar to that we have used for the mirror. So it's positive when the center of curvature is on the right side of the vertex, and it will be negative when C is on the left side of the vertex point. V stands for vertex point. Well, for plane surface, basically, you just put r to infinity, means on this side equates to 0. So you just left with the left-hand side of the equation. In other words, s prime is actually equals to the negative of n2 over n1 multiplied s. And this was the apparent depth that we worked on previously. Now, the tip here to remember again, whether it's a real or virtual image, is that for a refracting surface, the image, if it's formed on the other side of the refracting surface, then it's real. Okay, but for a mirror, if the image is formed on the same side of the object, then it's real. So that's easy to remember, I think. This is an example. You have a real object which is in air. This is air. It is at 30 cm from a convex spherical surface. And on the other side of this surface, you have water with a refractive index of 1.333. And the curvature of this curved surface is, it has a radius of curvature 5 cm. And so let's find where's the image and what is the magnification of the image. So let's use the equation, the refracting equation that we derived earlier, which is given here. So substituting n1, which is 1, s, which is 30, is positive, plus n2 is 1.333, s prime, well, we don't know yet. That's equals to 1.333 minus 1 divided by r. Now, for r, center of curvature is on the right side, so it's a positive value. So we have positive 5. So it's 0.333 over 5. In the end, you'll find that the image distance s prime will work out to be 40 cm. Since it's positive, so it's on the right side behind the refracting surface. And it is a real image. And now we want the magnification, and that we substitute the values into the equation that we derived from magnification earlier. So n1 is 1, s prime is 40, n2 1.333, s is 30. So that gives us -1. So this image is the same height as the object, and it is inverted with respect to this object. And now if we will introduce a second refracting surface, well, that makes a simple lens. You only need 2 refracting surfaces. And let's say that the second refracting surface is at 10 cm away. So the thickness of this lens is 10 cm. So we already found out where is the image of the first refracting surface. When you add a second refracting surface, this image becomes now the object for the second surface. And if you look at this diagram here, the second object now is actually on the right side of this surface. So we're going to take it to be virtual. Okay. And we did calculate that this is 40. Since this is 10, this will be 30. But it is on the right side of this refracting surface, so it is virtual. We will put a negative sign here. And using the same refracting equation, except the values are different now, because we will have n2 over s2 plus n3 over s2 prime equals n3 minus n2 divided by r2. That's for the second surface. So this is n2, this is n3. So n2 is 1.333 divided by s2. Now, though the second object is on the right side, but when we consider the refractive index of the medium, is the one before this refracting surface. So that's why we use 1.333. But the distance for the object, the second object, is negative. So we just substitute negative here, because it's on the right side, actually. So plus 1, now this happens to be 1 divided by s2 prime, and is equal to 1 minus 1.333 divided by, if you look at this surface, it has the same radius of curvature, except that the center of curvature is on this side. So the radius now will have a negative value, -5. So from this equation, you'll find that S2 prime works out to be 9 cm and is positive. So which means that we're getting a real, the second image is real, and it's on the right side of this refracting surface, which is actually here. Lateral magnification of the second image. So substituting the values. So we have negative, it was n1 in our original equation. Now because n2 over ns, now for the second refracting surface, the magnification will be equals to n2 over n3 multiplied by s2 prime over s2. So that's 1.333 divided by 1. S2 prime is 9. S2 is -30. So substituting into this, we get a positive, and it's 0.4, which means that this image is 0.4 times the size of this object, the second object. Then if you want to compare the size of this image to the original object, you will have to multiply m1 and m2. That was -1 multiplied by 0.4, it becomes -0.4. So in other words, the final image here is 0.4 the size of the original object, and it is negative, with the negative sign here, it is actually inverted with respect to this original object. Here is positive sign because we are comparing this to this, so their orientation is the same. Let's look at lenses. It will be bounded by 2 spherical surfaces. So for the first surface, we have the refracting equation, n1 divided by the object distance, that's from here to here, plus n2 divided by the image distance. As from the previous example, this is where the image was formed. So S1 prime equals to N2 minus N1 divided by R1. And then we look at surface 2. Now we have N2 divided by object distance, which happens to be from here to here, which is S2, plus N1 divided by the image distance, which happens to be formed here. So this will be the image distance, S2 prime. And that's equal to N1 minus N2 divided by R2. And in our sign convention, again, may I repeat, the radius of curvature will be positive when the center of curvature is on the right side, which is on this side of the vertex. And for real object, it will be on the left side of the refracting surface, and that's positive distance. If the object is on the right side, then it will be considered to be a virtual object with negative S. And for image, is a real image if it is formed on the right side of the surface, and it will be a virtual image if it is on the left side of the surface, and that's given a negative sign. Now, the second object distance, S2 here, would actually be T minus S1 prime. And in a thin lens approximation, we can take T to be close to 0. So therefore, S2 would then be equals to negative S1 prime. So let's put this relation into the refracting equations. So for surface 1, we can then substitute S1 prime with S2, that's negative S2 here. And for surface 2, we have this equation here. And when we add these two together, we will have, now adding this to this, these two cancels off. We have N1 over S1 plus N1 over S2 prime equals to N2 minus N1, which is common, into 1 over R1 minus 1 over R2. So in this case now, S1 is the original object distance, and S2 prime, which is over here, that would be the final image distance. So we can drop the subscripts and write as 1 over S plus 1 over S prime is equals to N2 minus N1. Now, N1 over here is brought over to the other side of the equation. And that's N1 here into 1 over R1 minus 1 over R2. And when the object is at infinity, we know that the image will be formed at the focal point. So S prime will be equals to the focal length. When the image is at infinity, that means our object is at the focal point again. Then S would be equals to the focal length. And if we substitute this into this part of the equation, so when S is infinity, this becomes 0. Then we have 1 over F is equals to this expression. And when the image is formed at infinity, then we also have 1 over F equals to this expression. So therefore now, this is equated to 1 over F. And this equation is called the Lensmaker equation. And for thin lens equation, we have 1 over S plus 1 over S prime equals to 1 over F. These are examples of thin refractive lenses. So this is a biconvex. This is a planar convex. This is a meniscus convex. The center of curvature of both these surfaces are on the same side. These are converging or positive or convex lenses. For diverging or negative or concave lenses, then we have biconcave, we have planar concave, and we have also the meniscus concave, whereby the center of curvature for both surfaces are now on the left side. This is an example of aberration-free lenses whereby the surface are not a sphere, but they are in the shape of a hyperbola. We shall now draw ray diagrams for thin lenses to locate the image. So this is a convex thin lens, and it's represented by an arrow this way. This is the optical axis. So if the object is placed here, we're going to draw the first ray. that is parallel, that comes from infinity, so it's parallel to the optical axis, passes through the lens, and it will then bend and passes through the focal point. The second ray will be aligned to the focal point, reaches the lens, passes through the lens, and now it is parallel to the optical axis. At the point of intersection, we locate the image. There would be a third ray that we can use. That's an undeviated ray that comes from the tip of the object, passes through the center of the lens, and will also meet at the point of intersection here. So any two of these three rays will be enough for us to locate the image. For a concave lens, we represent it differently. As you can see here, the arrowhead is an inverted V. So if the object is placed here, we again draw the first ray, which is parallel to the optical axis. Passing through the lens, now it diverges, but we aligned it to the first focal point, and this is the ray. The second ray will be the ray that is aligned to the second focal point, but upon passing through the lens, it will now become parallel to the optical axis. So projecting this transmitted ray backward, it will meet the first ray and this point here, and that's where we locate the image. And of course, we have a third ray that passes through the lens undeviated. So align it through the center of the lens. So this will be the third ray, and this ray will also pass through this intersection point here. The lateral magnification will be given by the height of the image over the height of the object, or the image distance over the object distance with the negative sign in front here. Now, this diagram tells about the nature, the location, as well as the magnification of the image formed by convex as well as concave thin lenses. Let's take an object from infinity towards this distance 2f. So this object is real, and when the object is at infinity, the image will be formed at the focal point. And this image is real, it is inverted, and its size is smaller than the object size. This distance here is shorter, this distance here is longer. So as the object is brought nearer to 2f, the image will then move away from the lens towards 2f. And as nearing 2f, then it starts to enlarge quickly until at 2f, it will be the same size as the object at 2f. Now, as the object is brought from a distance 2f to f, then the image will still be inverted, and it will get larger, and it will be formed further and further away from 2f until it goes to infinity when the object is at f. And then as the object is brought nearer than f distance, then the image now becomes upright and is virtual, and it will be brought from infinity, and it will be brought nearer towards the lens as the object is placed closer and closer to the lens. The size is larger than the object. Next, we look at the diverging lens. That's the negative lens, or we call it concave lens. In this case, the feature is the same no matter where we put the object. So you bring an object from infinity, a real object from infinity, up close to the lens, you'll find that the image is always virtual. So formed at the focal point when the object is at infinity, and then it will come closer and closer to the lens as the object is brought closer to the lens. And the size is smaller than the object, and it is upright and virtual. we have come to the end of lecture 4. So at the end of lecture 4, you should be able to use ray diagrams to locate the image in mirrors. You should be able to use refraction at spherical surfaces to derive the refracting power equation. And you should be able to derive Lensmaker equation as well as the thin lens equation. And you can apply the lens equation to find the image for a lens system. And you should be able to apply ray diagrams to locate the image in lens systems. Thank you for listening.